analytical data to YouTube. It was published this year on VLDB by the Google people. It's an industrial track paper, but I found it quite interesting to present today.
That's a question.
May I briefly interrupt?
Yeah.
Since I wasn't here Tuesday and yesterday, quick question: has Tanya been introduced? Do you know
I
each
walked
other?
around.
You walked around. Okay. Thank you.
Okay. So let's start then with the introduction. So over the years, Google has developed a bunch of systems to handle their data on YouTube. And for each system, they had a paper about it. And this, as a result, they had like 6 papers until 2017. And for each paper, a specific system to solve a specific problem they had. They have basically 4 use cases on YouTube, and they used all the systems to solve that.
But they're not only YouTube.
No, not on YouTube, for everything.
Yeah,
But,
because F1 is
Yeah.
as well.
But for in the case of Procella, that's the one that they are proposing. It's basically used on YouTube right now. And the question that you might ask is, why do they need another system if they already have a bunch of them? Well, I also had this question, why another data processing system? And the basic problem they had was they had too many systems.
So the solution is one more.
Yeah, they did it because they use it. The thing is, they had this growing scale of data on YouTube, which is, they had the real big data there, and they had too many systems to handle that data. And they had to communicate, they had to perform some communications between the systems, and each system has a different type of data format. And to solve this, they had to choose one unique system to solve everything. And which use cases are there? Well, basically these 4. Reporting and dashboarding, embedded statistics, monitoring, and ad hoc analysis. For each one of these use cases, they had one system before, and now they have Procella running for the past 2 years, I guess, or more than that. Now let's go for each one of the use cases. The first use case is reporting and dashboarding, which is basically the user's perspective. YouTubers produce videos there, and they want to know information about their fans and such. And they have this tool where they show some information about some statistics about videos, and this is translated to tens of thousands of queries per second. And it's basically a set of filters, aggregations, and joins on queries. But the problem is that they need to show this near real-time response time. So it's quite a challenge for them. The other use case is embedded statistics, is the amount of likes and views they have on videos. And from the system's perspective, this is high cardinality queries. So they basically have to count on real time how many views that video has, while a lot of people is watching it. So it's quite a problem for them, because values are constantly changing. And this is translated to millions of real-time updates concurrently. And again, in the first use case, they had this kind of OLAP scenario, and here they have a OLTP scenario. So it's kind of a hybrid workload.
Just a quick question.
Yeah.
How is that a high cardinality query? If you can't I suppose they update some counter, or do they just record every single view and aggregate over that?
I think they do this in a distributed manner, right?
Mm-hmm.
So they probably aggregate on the distributed server, and then they update to the
Okay.
to the row.
Well, I think, well, I don't know. But what I would do if I were them was to consolidate like these as views, basically for every video that counts. Because if so many people are viewing it, you have to produce this number
Mm-hmm.
in very many different screens as well. So it doesn't make sense to actually recalculate it for every of those screens. So I suppose this is,
Yeah, they don't mention so deeply how they do it.
this is probably in some kind of view that they consolidate. Yeah.
Okay, the next one is the monitoring. This is an internal use case because it's basically performed by Google people. It's very similar to reporting dashboarding. They also have these statistics for the employees to analyze how YouTube is performing. And the query volume is often low because only a few people have access to this. They do some downsampling because they have too much data and they want to basically reduce the amount of data they have to process. So they apply downsampling, which is a technique to reduce the amount of data in a stream. And they also analyze how to expire old data, because again, they have too much data. And they also perform some efficient approximation and time series functions there to analyze trends and such. The last one is the closest one to our topic, which is analyze trends in their products, in this case on YouTube. And it's also an internal use case. All the engineers use this tool. And low volume queries, moderate latency. They don't really care much about how much time it takes to run the queries. But most of the queries are really complex because they are analytical queries. And the problem in this case is that they had to develop a system that was able to not only be fast, but also to be available for multiple updates and such. So it was quite a complex architecture. And that's why they developed this Procella. The basic idea is to implement a superset of capabilities required to address all the 4 use cases and kind of decrease the bottleneck they had to communicate between all those systems. In order to understand how Procella works, we have to understand also how the Google infrastructure works there. Procella runs on the Google infrastructure, and it communicates with Colossus and Borg. Colossus is their distributed storage system. Like they have all their data spread across multiple data centers, and this Colossus is the one that manages all their data. In this system, data is immutable, so they basically only open files and append data to that files. The metadata operations have higher latency because they also store the metadata on the distributed system, but they cache the metadata to improve performance. And all the operations are remote operations because they have to access from multiple servers.
It's like some kind of S3.
Yeah.
Essentially.
And the clusters run on top of this board. This board is basically the system that manages how the queries will be distributed over the data. In this system, vertical scaling is a challenge because they have multiple machines running on clusters, and they really don't know how are the configurations of those machines. They also have to bring down some machines for maintenance every now and then. And even with less machines, they still need to keep the performance as equal as it was before. And that's why the performance is unpredictable whenever they are running queries there. Procella data, how the Procella stores the data. Procella is basically a database, right? So it stores the data logically as a table and physically as columns, like in a columnar format. And the metadata, they implement all sort of modern data structures. That's how they call it, like zone maps, bitmap, and blue filters. And they implement most of the SQL standard. And to ingest the data in the system, they utilize this batch ingestion. They have a server that every now and then checks the data and ingests the data in a batch, with batches. And it's on real time because they produce a lot of data. They also have this compaction server, which checks the...
But sorry, batch and real time usually are opposites. So it's either batch or real time. So, or is it both?
It's both.
Depending on the use case.
They do both. They have a real time and batch.
Okay.
And compaction, they have this compaction server which checks the write-ahead log and then analyzes how it's going to compress the data, compresses the data in a different format, and they use this multi-pass compression, which they first pass. They form a first pass over the data to analyze their statistics and to get some information like number of distinct values and such. And then they perform another pass to actually compress the data.
And they do that for every piece of data that they compress?
In the write-ahead log, yeah.
Is that similar to this Aurora system?
Sorry?
Is it similar to this Aurora system at Amazon where they also
Not really.
have this kind of background system that looks at the val, no?
No, because I think Aurora is more like a block manager that could also be a drop-in replacement for the data format supported by MySQL, which is basically what it's created for. It's a storage subsystem for MySQL, so it's not changing the bits that are actually on that in that log. I was asking because, like in Vectorwise, we had this compression wizard, which was invoked not on every block. You know, so you would look at at some batch of data, you would calibrate what compression method to use, and then you would use that for actually more data. But this is actually looking at all the data every time it calibrates again.
Yeah, the first pass they do in all the data.
Yeah.
And then the second one is only the ones that they identify as possible to compress.
Well, the second task, then they are compressing the data. I suppose.
Yeah.
Then they are actually compressing the
Yeah,
data. Yeah. Funnily enough, customers of Vectorwise, they really cared so much about compression that they used the maximal setting very often, where they would compress every block, always. Wizard every block. So that's basically this setting.
Okay.
Anyway.
This is a big picture of how the Procella system works. We have here the query client, and the query client issues a query to the root server. The root server reads the metadata from the metadata server and uses this information to prune some scans, to prune some data during the scan. So they know that they don't have to scan those files that are in specific data center. The data server is the one that performs most of the heavy work. The root server do the parsing, the planning, and optimization of the plan, and sends the plan to the data server. The data server then executes the queries, actually sends the queries to the Colossus, and then in the Colossus they execute the query locally. They claim that...
So sorry, they execute the query in Colossus?
Yeah, they claim that they push down the computation to the data by doing that. That's the main claim of...
You cannot do that for all the computation. You can do that for filters, but if you do to join two tables?
Yeah, then they have like four or five types of joins. Depends on the amount of the size of the fields and the...
But where do these run? Not in Colossus.
Sorry?
Where do they run, these joins?
They depends. They usually run the data server.
Okay.
But depends on the size of the relations. Most of the paper, in most of the paper, they claim that they do this push down of operations to the data.
1 second before you continue. Sorry.
Sure, no worries.
It says remote memory there. What is the role? Do you know what the role of that is?
remote memory.
They're on the side.
They have this remote memory to cache information. They cache metadata and the data itself in this remote memory. But I don't know where they put this memory.
So it's like a memcached maybe?
Yeah,
Okay.
something like that. Yeah, now we go for the optimizations they have, the caching, the data format, the evaluation engine, the partitioning and indexing, and the distributed operations. Caching. Okay, the basic idea of having like immutable files is because you can cache and you don't have problem with invalidation because you won't change the files, right? And they do this because they cache all their metadata and also the headers of the files. And they have a different caching infrastructure for metadata and data, and they cache both to allow that pruning during the scan. They also have this affinity scheduling where by analyzing the metadata they know exactly where they need to run the query, so they only send the query to be run on the servers that they know the data is there. Otherwise, they don't send the query. It's interesting. They have a different name for each part of the system. The data format they call Artus. It's a heavily optimized data format for where they keep pre-computed data as well. Again, they do this multi-pass encoding. Then they are able to have this cluster encodings there. In the first pass, they go through the data, identifying opportunities for compression. Then the second pass, they actually compress the data. They also sort columns to optimize like for run length encoding. And this allows them to have lookups in logarithmic time and 6 in big O1. They have this tree representation for repeated data types that I didn't catch. They only have one paragraph explaining that. And what they claim is that they use this to identify whenever you have a repetition in your data type. They keep this structure for the schema, but that's the only information that I could get from there. And that's one of the main differences from the previous data format they had. They also expose the encoding information, like in run length encoding, they expose the information to the query engine, and then we can perform some compressed execution there.
Did you understand from what you read what repeated data types are? I don't. So.
No, I didn't.
I think this is like nested tables.
Yeah, I think so.
Oh, okay.
Sounds like it. Hey, about this ordering, so, okay, great, so they sort stuff, but what do they sort on, and how do they decide what to sort on?
They didn't mention exactly what, how they decide that.
I've read that part, but I'm not sure they actually sort something for compression. It's just that they have compression that works well when stuff is sorted, and they say that they can still do random access then. And they say it's in O1, but it's not really O1, it's in O of the block of.
Yeah.
They have like a sort of an index on top of it. So they have these checkpoints for delta compression from early as well.
Okay.
But I don't think they actually sorted just to be
Before,
able to compress.
just for compression. Yeah.
But yeah, they need this random access because they don't want to be just analytical data, but also,
Yeah, well, they
For
mentioned
else
they
business.
use this for inverted indexes, so I suppose these are sorted,
Mm-hmm.
and then you want to do low latency lookups with that.
Okay. Here they have a comparison of their new data format against the previous one, and they basically compare their new system with the previous one. And they show a big improvement in performance. In memory, they keep R2s uncompressed, and on disk it's compressed. So the uncompressed format in memory is almost the same size of capacitor compressed on disk.
So it's very compressed. Hey, is this system implemented in C++ or?
C++.
Okay.
And these queries, what are those? Do you know?
These queries are, Oh yeah, I forgot to mention. The first query is a pure lookup. The second query is a moderate filter. And the third one is a full scan, and the fourth one is a group by with aggregation. These are the basic queries they have on their workflow.
So this is just comparing the file, the data format, or is this the whole system?
Only the data
Sorry,
format.
okay, yeah.
So, if the third one is a full scan, so is the decompression and capacitor so expensive? Because you have the full scan, you have like the data size. If you just look at the data size, and maybe it's in this, I don't know, and the difference is not that big, but we get a factor of 4+ in performance difference.
So they don't
It's
mention.
obviously not from data access.
Mhm.
And if it's a scan, then there's not much else going on other than decompression.
It could be the exposure of the
Yeah, like compressed
compression
execution.
to the, because otherwise you have to decompress for a point lookup, right? If you
Well,
cannot
it's-
do this, if you cannot do
It's a
compressed
scan, so it's
execution.
not a point lookup.
But the first one was a point lookup.
The first one,
Yeah,
yeah.
the first one is.
Are you talking
Yeah, the other ones they're more complicated to we need to think more, but that one was kind of hitting me. It's a scan. The
Oh, yeah.
scan is not much, scan is rather predictable in terms of performance.
Or is it row versus column, maybe?
Well, it could be as well with columns, so yeah.
Yeah, it
Well,
was,
okay,
it's
that's
row
that's the
versus
whole,
column.
that's the whole data set, and less data is accessed in
Yeah.
outers. Okay, that could be, yeah, okay.
Yeah, capacitor was implementing a row store man.
Okay.
Ah.
Yeah.
The evaluation engine. So when they were thinking about how to implement the evaluation engine, they thought a little bit about LLVM to use some sort of compilation there, just-in-time compilation. But they found that it would be a problem for the OLTP scenarios, because then compilation could be a bottleneck for them. And then they decided to only rely on C++ template meta programming, only to generate for different data types, like mark data on DuckDB. And they call their engine Superluminal, and it's basically the analytical engine that runs on top of Procella. They don't have intermediate materialization, and the optimizer is based on a hybrid approach, where they have some rules, and also some they adapt to the data. They analyze the data and adapt the optimization based on that. So it's kind of static and dynamic.
It's a strange reasoning, so
To not use LLVM.
to not use compilation,
Yeah,
because
that's
usually the argumentation is exactly the other way around. Like,
Mhm.
I want to keep if it's only analytical, I want to keep the system simple, so I use vectorization. But if I need OLTP, then vectorization doesn't help so much, so then you might actually do LVM, as long as you know what transactions you're going to run, like if they are storage procedures, for instance. Then you can actually be very fast.
Yeah, that's what they thought. Okay.
It's fine, vectorized.
Partitioning and indexing, they have a lot of indexing implementation on that, because it's mainly a distributed storage, so they need the indexes to optimize the lookups. They have this multi-level partitioning and clustering, and they partition like fact tables by date, and the dimension tables are sorted for the indexes, like Richard has mentioned. And this basically helps for the pruning, because then by reading the metadata, by reading the index information, they are able to prune some files that they don't want to read during the scan.
So this is really hard coded in the data partitioning. Interesting. So basically then they have to write their queries around that as well, right? So then this works best if then the queries, there's some sort of restriction on the date.
Yeah, more or less. But I think for their use cases, they basically rely on dates, right? Like for the monitoring and for the doc analysis.
They're
So-
just building a business system for themselves, right? So
Yeah.
they can get away with this, I guess.
Mhm.
I think they build this is for themselves. Yeah, that's true. Here it's interesting. They have like 5 different joins, and it depends on them where the data is and how big are the relations. They have this broadcast join, which as the name says, broadcast the operation to the data servers. So you have the one side in one data server, another side in another data server. So they first perform the join in one data server, and then there is the build side, and then they perform the lookup in another data server. The core partition join depends on the size of the size. If one side is small and they have a partition on the tables partition, they can basically load each partition in the data server and performs the joins per partition. The shuffle happens when both sides are really large and they don't have partitions, so they shuffle for intermediate servers. And the pipeline join, I don't recall this one though. I have to check a little bit. Oh, okay, when they have complex operations with the right side, they first they push down all the operations they can, they execute the operations on the data server on the right side, and then they send the result to the left side. And the remote lookup I think is the slowest one, because they have to do some remote access between different data servers. Now the main experiments. In this first experiment, they are evaluating DeepCHQ1. The Superluminal is the new system, and the Supersonic was the previous system they had, the query engine. And they show here how good they are now. But they also implement a C++ optimized version to show there is still some space for games. Here they evaluate the different data formats. They have a capacitor and Artus running with Superluminal, and also they use some C++ array format to show how be the result of this implementation. They also evaluated over the whole DeepCH.
Still slow, by the way.
Yeah.
This reading is slow.
That doesn't matter because there's 1,000 boxes doing it.
Yeah.
Right?
Yeah,
I mean,
I
that's
think they
probably-
did the
yeah.
evaluation with 3,000 cores. Here they evaluate the scalability of Procella, how it scales. If you perform like DeepCH, scale factor 1 tera and 10 tera. And they have 3,000 cores and 20 terabytes of memory. It's interesting because even with a lot of memory, they are able to fit only 2% of their data set in memory. And if they were able to actually fit everything in memory, it would be in-memory database entirely.
But only 2%.
Only 2%,
And they had 20 terabytes of memory.
20 terabytes of.
Good. Okay.
No, but this 2% is for their entire system, right? Not for the experiments. For the entire data they have, the entire memory they have.
Yeah, okay.
They only are
On
able to
their
fit
YouTube
2%.
data.
Yeah, the YouTube data.
Okay. But here it's in memory then, effectively.
Yeah, here is in memory.
But that's the YouTube data, but that doesn't include the actual movies, right? That's only their
Yeah, database.
administrative data, they're only their statistics.
Mm-hmm.
Sure.
And the last one, they run DeepCH 10 tera. They want to evaluate the throughput with 10 streams. And they also calculate the joining, which is like 2 seconds for the difference between the streams and Power Run Extend. I didn't get what was that actually, Power Run Extend, if you guys got it.
No, well, is that when they would just extrapolate, do a power run, and then multiply all the times by 10.
Oh, probably, yeah.
And compare that to
To
running
10
the
streams.
streams concurrently with each other or something like that.
Mm-hmm. Yeah, they didn't explain that.
Yeah.
And also in the previous one there was like Procella 10T versus Procella 1T times 10.
Yeah, I think it's a typo.
No.
No,
It is.
I think they did. I mean, that's what my interpretation. That they did 2 runs on the 2 sizes, but here they display them in one graph, and to kind of normalize them, they multiply the results of 1T by 10.
Okay.
Well, that would be linear scalability.
Oh, I see. They didn't actually measure the.
I just scanned this paper when it came out, so I don't know. So I'm just interpreting this graph here.
Yeah.
I don't know.
Okay, the
Maybe
caption
I'm
says then 1T expected execution time versus 10T execution time.
Oh yeah, that's true.
That might be indeed split up.
Okay. That's it. These are the conclusions. Like their claim that a movie computation today improves performance on distributed and non-distributed systems. Exposing the compression format to the pre-engine brings benefits with compressed execution. Custom code schemes allow flexible data representation for them, and on distributed systems caches the main approach to avoid network penalties. These are the main conclusions that they had. I think it's also plausible.
Did they do experiments to show that exposing the compression form to the query engine actually brings benefits, or is that just something they said?
No.
Well, they have some more detail on it. You actually, I had expected you to focus on it because of your white box compression.
Mhm.
Right?
But they didn't have much details on that.
No, well, they just say that if you have RLE, they encode it as related encoding. They encode it as 2 columns, one being the count and the other one the value,
Yeah.
explicitly, rather than having some black box RLE. Same thing with dictionary encoding.
Mhm.
It's like some dense offset called integer, and then some mini table, which is the dictionary, which is exposed by artists rather than treating this as a black box compression.
Yeah, but they didn't actually evaluate. Like,
Yeah, what happens? So how they? Well, but you can kind of imagine that you
Mhm.
can kind of.
You could compute aggregates easily, I guess.
Yeah, or I think you can push down selections. I think that's one of the things that they would want to do, without like having to. I mean, like a selection on a dictionary column. Obviously, you first look up the value or the range of values in the dictionary, and then it becomes an equality or a range, or an in clause, and then you evaluate the in clause on the integer. Okay. It's the obvious thing that you would do for pushdown. But yeah, you can do it without special tricks if your engine understands dictionary as being 2 columns or other 2 tables even. And with RLE, I don't know. I mean, yeah, I suppose that you can do like selections. Again, you can first look at the value column, do the selection on the value column, which is much smaller, and then only expand the result for the selected values.
If we're doing aggregations, even better, right? Just
Yeah.
count the number of values there. Okay,
Can you do this
that's it.
in your schema, SQL schema, and hope that your SQL optimizer is smarter? You can put the transparency that high up.
Yeah, I think these are still kind of pre-filtering rules that you
Like
optimize
applying
it.
white box compression in the schema, I mean.
Not here, but generally, if you think that far, you can think the next one.
Okay, any questions?
Yeah, what did you think?
What did I think?
Well,
Well,
you're convinced you're gonna join Google to work on the system.
I could. It sounds interesting to work with because they have like both OLAP and OLTP in one unique system. But I still think there are some benefits on having like a specific system for a specific use case. But for them, the main problem was the ETL pipelines. Like they have a complex ETL pipelines because of the different data formats. but once you have the same data format for multiple systems, this is not a problem anymore. So I think it was a nice approach, or they just wanted to have another paper.
So
But they are using this.
did they do the analysis in their paper, or otherwise
Mhm.
it might be interesting to read it from that point if the paper gives sufficient information about that. So they started out like, hey, we have lots of systems, they all do a great
Mhm.
job for a specific task, but now we need all these tasks together, but orchestrating all the systems is the bottleneck. So we need all this functionality together. So, and we build a new system. How does each of the single tasks in the new system compare to the original systems or to the specialized system they had before? How much compromise did they have to do to get it all under one umbrella to compare to the specialized systems, if at all? Or the other way around, how simple was it to, instead of having whatever high-level standard interfaces that do the orchestration, put them together and put the communication on a lower level, and making them one way or another talk to each other on a lower level. It seems to be that all these systems are largely new implementations compared to what they had before. I'm not that familiar with their complete stack, but
Yeah. What they claim also is that some of these systems couldn't scale anymore because of the amount of data. So it was not only the problem of the communication, but
Okay.
also the amount of data they were handling. And they don't have experiments showing how it was before, but they claim that it's faster and more interesting for them.
Okay.
So I think what is interesting, I mean, what we have heard so far is a rather well done analytical database system with columnar storage and like disaggregated storage, like as in the cloud. Their claim is that they should be able to do also OLTP, like these transactional workloads. And well, so for that, if I read this correctly, they have this ingestion server, and what this does is that indeed all the small updates are immediately logged. So
On the right hand log, yeah.
or well, actually, they could imagine that you cannot immediately log them. That would be too much, but probably. I actually don't know what kind of transactional safety they really, because you would not want every click to be logged. I still cannot imagine it. I think that still must be the case that every 1,000 clicks, every 10,000 clicks, they might write some page to the, because this is in Colossus, like this long. But what they also say here is that immediately they have some partitioning scheme. So if you have a table like this that is being updated and updatable, then they have an in-memory partial copy of it partitioned over data servers, and then so what they're doing is two things. So the transaction commits, which means it gets to a log page, but it also is sent to the correct partition, and there they keep like an in-memory table with all the hot data, but not all the hot data, because in the background there is a compaction service that compacts the log. So when the compaction service gets to the logged page, then supposedly I think they can send a message to the data server saying you don't need to hold these tuples anymore in memory, you can drop them, otherwise the memory would get full. So they have something like that. So that for some tables they can set something up that like all the updates will be buffered in memory using some partitioning scheme, and there is this write ahead log that's getting compacted. So that's what they did, I think. That's the novelty, maybe. Well, it's not really novel, because it's
It's not, yeah.
it is what is proposed in a write store, read store in a column store. That's it. But then put into their architecture and infrastructure. Yeah.
Any more questions?
anecdote about this system is that there is a bit of a database war inside Google. So there is the biggest clan is the F1 clan, and this is the second biggest clan, the YouTube clan. And then there was the kind of the power drill Dremel clan who were in ETH, and they have been scalped by the YouTubers. So they were actually also working on a system. That system got cancelled recently because of their potential customers chose to adopt Procella instead. And Procella is so successful that it's already also achieved that the F1 team is also switching the data storage to Artus. So as F1, it's kind of made out of components, so you do not have to adopt Procella fully, but the storage part of it is also is now being adopted in F1 as well. But the Procella people, they think that it could also replace F1, but the F1 people don't think so. Yet.
I didn't know they had this kind of wars there. Okay. Any more questions?
I have one tiny question.
Okay.
I think it was on the first slide about Colossus, where they, give the
This one?
What we hear? Yes. Measure data operations have higher latency. Higher than what? Higher than data operations, or higher than they would have if they were just local?
Higher than it if it was local, because it's basically remote access,
Yeah,
right?
okay.
That's what they claim.
Which is obviously not surprising.
Well, in S3, listening cost is always typically quite high.
Yeah.
Just doing an LS on the bucket. That kind of stuff. And Borg, that is their like Kubernetes powered
Container.
cluster manager, container manager.
Okay, any more
Okay.
questions?